Okay. So let us begin. Can you maybe go to...
So
Okay.
I cannot see my
Yes.
mouse.
Yes.
The...
So it's a pleasure to have Cristian Joana as our next speaker of this week's Majorana-Raychaudhuri seminar series. And he's going to talk about initial condition problem of inflation in full numerical relativity. So maybe I'll send you a reminder when 5 minutes are left.
Okay. So should I start?
Yes, please.
Yes. Okay. So thank you very much for the invitation to this seminar series. I'm very happy to talk here. So as the title says, and the nice introduction, I will be talking about the initial condition problem for inflation and how we have studied this problem using numerical relativity simulations. So let me just first start with a brief introduction to numerical relativity. So as we know, it's been very clear in the last 10 years, numerical relativity has been an important tool for gravitational physics. A common example is we are able to compute the gravitational waveform from binary mergers, right? This has been quite extensively used by LIGO-Virgo-Cagra collaborations, and it has been very successful in that regime, astrophysics. Also, there are other applications of numerical relativity beyond astrophysics, so not only in supernova, binary mergers, etc., or black hole physics, but also in cosmology and fundamental physics. So I'm going to be talking today more in the cosmological part. And yeah, so we can also treat a full numerical GR code in order to study scalar field cosmologies or initial condition of inflation, like I will show, or in the future has been also done quite extensively the study of primordial black hole formation, exotic compound objects like boson stars, etc. Also, fundamental physics has been lots of application for this CFT, holography, GR in extra dimensions, etc. Today, I'm going to be talking more on the cosmological side. So as all we know, so numerical relativity, what we want is to solve the full GR Einstein equations in the grid, so in the computer. And by that, basically, we have to solve both the evolution equations by the space-time dynamics and the matter dynamics, right? So I'm going to just briefly introduce. So we do just a space foliation of the Einstein equation. So we decompose the metric in this 3+1 manner, where this gamma tilde is the metric of the three of the spatial metric. So as in the picture shows, basically we have this manifold of a four-dimensional manifold. We do slices, and basically what we do, we reduce the problem into an initial matter problem. So when we project Einstein's equation into this kind of projection, we obtain basically four constant equations. So there's the Hamiltonian and the momentum constraints, and some evolution equations that are particle differential equations that depends on time. So basically, we can evolve from a time set t1 or t0 to the future, basically. Okay, so that's basically numerical relativity. And just to give a very easy example to understand is basically we take the constant equations, and then we solve the initial surface. So in this example, it's just two neutron stars in vacuum or in a Minkowski space. We put the neutron stars, and then we have to solve the Hamiltonian constraints and momentum in order to create basically the metric and the gravitational interaction between these two bodies. And of course, all of you put the momentum. So if we evolve this initial configuration, clearly the neutron stars, the stars are aspiring, emergently will be merged. So in order to do that, we use this evolution equation that I just described above. And eventually, maybe it will form a black hole, all the gravitational wave will be emitted. So basically, we can extract physics from these simulations. That's why they're very, very interesting. Why we use full GR. We don't have any simplifications in the dynamics. So that's basically what we do. So of course, I just summarize very quickly, and I didn't go into the details where it will become more complicated, but just to have an idea, that's what we do. And also just to basically say that in cosmological simulation, we do the same as the astrophysical case, but only in a more, instead of having compact objects that oscillate, etc., we have a highly dynamical space-time evolutions, and we want to answer some questions. Okay. So again, very quickly, just to illustrate the magnitude of how complicated this partial differential partial differential equation are. So basically, we have to solve the matter sector. So here is just the energy momentum tensor for a scalar field, because I will consider inflation, right? So this is the T mu nu for a scalar field, and we have the energy density, the momentum, the stress, etc. So this in rho, Si, Sij, etc. And then we have the space-time variables, which is in the 3+1 for this composition. Now we have this spatial metric, gamma Aj. We have the extrinsic curvature, which is basically the time derivative of the metric, or like momentum of the metric, if you want to express it that way, where this Aj will be the traceless parts, or will be tensors and vector modes, like gravitational waves, if you want. And in this case, just the trace, which in our cosmological dictionary, this case is just the expansion rate. So a negative k will be a positive h, Hubble rate. And then in the bottom, we have the constraint equation. As I said, this Hamiltonian momentum constraint that we use to create the initial conditions and to monitor that the constraints are satisfied. So Einstein's equation are satisfied at each time level, each time evolution. Okay. So in order to evolve this system, we have the time evolution. So from the matter sector here, we have the Klein Gordon, which comes from the T mu nu, just analytically. From the space-time variables, so basically we have all these 3+1 formalism, where we have basically the conformal factor, this chi, this guy is similar to the cosmological scale factor, local version of cosmological scale factor. And gamma Aj, as I said, is the spatial metric. K is basically the expansion rate, or the Hubble rate, if you want. Aj could be tensors, and etc. So basically, we have to evolve all this system, all these complicated partial differential equations. And in order to do that, we have to choose some nice coordinate gauge in order that if you form a black hole, you don't resolve inside the singularity, etc. So there are some nuances that you need to take into account, but I will go there. So it's just to show a picture, basically all the equations that we need to solve in the computer. Of course, maybe you do this in the laptop will be very costly and will take forever, but you need high performance computing, so a big cluster where you can run several nodes. And to do that, basically, you have questions on astrophysics or cosmology that involve strong gravity and non-perturbative dynamics. Then, in order to obtain questions that you cannot do analytically because they are not perturbative, the way is to use numerical relativity. Even it might take some time for the simulations to get you the answer. But that's what numerical relativity does, and that's what we do in this study that I'm going to show. Okay, so as I said, there are many projects on numerical relativity. So at the moment, I'm working more on primordial black hole formation, but today I'm going to focus on the first topic, so homogeneous initial conditions for cosmic inflations, and I'm just going to motivate why we care about this. So as we know, the standard cosmological model and the CDM gives us a very nice picture of the current universe. So we're starting from the radiation domination and the Big Bang plasma, expanding matter domination, now dark energy. All this we know because we fit the CMB power spectrum, the temperature and polarization power spectrum. And basically, we can fit the power spectrum as incredible prediction, and this tells us basically the composition of the universe today, the problem of dark matter, dark energy, the current baryonic energy that exists, and yes, so basically all the information comes from the CMB. However, if we go back in time, we see that actually the sky, the CMB that we see today at the time of recombination was separated by 10 to the 4, 10 to the 5 Hubble patches. So this is very puzzling because, yes, indeed, the CMB is very homogeneous. So wherever you look at the sky, or you try to measure the temperature, you will have that the CMB has that 2.7 decimals kelvins, and the fluctuations are very tiny, 10 to the minus 4, 10 to the minus 5 degree Kelvin. So basically, how to explain this homogeneity when, in principle, this Hubble patch should be completely disconnected? So it's a question. Is how we can explain that actually the CMB is so homogeneous. If you go back in time, they should not be in casual contact. In order to solve this issue, basically, that's what cosmic inflation is. There are other alternatives of cosmic inflation, but I would say that cosmic inflation is, for the moment, the most preferred one. Partially because it explains these tiny homogeneities. So these tiny homogeneities are just quantum fluctuation occurring from inflation that basically leave the Hubble radius during inflation and then become a super Hubble scales. And yes, so basically cosmic inflation, what it does is a rapid accelerated expansion of the universe that occurs at the very early universe. And this rapid accelerated expansion, basically what it does is redshifted all the perturbations at super Hubble scale. So it begins at super Hubble scale, but then they get stretched very fast to a super Hubble scales. And this explains the large scale homogeneity and isotropy of the universe. So this is very nice model in order to explain why the universe is flat and homogeneous, and also it gives a very nice explanation on the power spectrum, why we have these inhomogeneities, why this is nearly scale invariant, and why the tilt is slightly redshifted. So inflation can explain all this. So it's, in that sense, it's very nice. So in order to obtain inflation, though, so basically what the easiest way and the simplest way in order to obtain inflation is just assuming that the universe at the very early was dominated by a scalar field. If you have that, and with a particular potential, basically what you need is that the equation of state, so basically this W that I'm plotting here is the pressure divided by energy density, is strictly smaller than -1, and this can be achieved with a single field inflation. So you have the universe dominated by a scalar field. If the potential is dominated, then you can see clearly that this omega goes to tends to -1 until the jitter. The jitter mimics the jitter inflation space-time. So this is exponential expansion. So yes, so in that case, it's very easy. But the question is, what happens if the initial universe is not homogeneous? It's not dominated by by the potential, but they also have important gradients and kinetic terms that fluctuate. So then that inflation can start or not, and that's basically the question that we want to deal. So just in order to be a bit more precise, what is my picture that I'm trying to have the mind frame that I have? Imagine that at the beginning we had this the singularity in the quantum gravity regime, where we simply don't know. We don't have a model that can describe this phase, but eventually, for them, there must come some kind of classical universe where the quantum gravity regime is not important, so we can use numerical tools in order to do GR, so just classical GR. And this pre-inflationary phase that here I put in blue is just a phase that in principle could be very homogeneous and very anisotropic and could have non-linear perturbations both in the gravity sector and in the matter sector, so it could be very complicated. And then the idea is that this phase eventually should lead to this inflationary phase, where basically the universe homogenizes as per Hubble scales, as I said. So the question at the beginning, this topic is quite old, no? So at the beginning, we say, okay, in order to have inflation to start at living 1 point, you need at least one Hubble patch roughly that is homogeneous, meaning homogeneous that is dominated by the potential of the scalar field. If this is fulfilled, then inflation will start and will rapidly expand, as here I illustrated in that picture, and will be larger than the Hubble regime. In that picture, the Hubble, I just picture it with this blue circle. And as I say, if this is fulfilled, then inflation will start, and in principle, it will homogenize the universe. So it's this fine-tuned. So instead of computing what is the probability to have a Hubble patch that is more or less homogeneous at the early universe, so what we do is, okay, no, let's not assume that. Let's assume the early universe is completely homogeneous. You don't have a Hubble patch that is homogeneous at all. And whether if the universe is expanding, because we are going to assume that from the quantum gravity regime, you live to expanding universe, it's enough to redshift all these perturbations and curvature, and eventually at some point one of these dots will be the potential will dominate and begin inflation. So that's the main question, and because this can be extremely strong gravity influence, you could collapse on certain regions, etc. Also, you have a nonlinear perturbations in the scalar field, and we need to treat this numerically. So that's basically what we do, and that's why we use numerical relativity to study this basic transition between pre-inflation and inflation effect in this frame. Okay, so this question, so what if the universe could begin or not in those homogeneous initial conditions? So this came, at least for me, when I really start thinking about it, is a paper in 2013 by Anna Paul Steiner, and collaborators. where basically they stated that basically inflation was in big trouble because if the initial conditions were just were dominated by kinetic and gradients, then this combination will block inflation from occurring. So inflation will be very fine-tuned, and then we cannot explain the homogeneity of flattened universe by this mechanism. So that was a bit puzzling. So I think, okay, well, let's try to do this numerically. We'll try to put it, and then try to see if this is true or not. And there are many. There has since then has been quite several groups already studying this question. And now what I'm going to put is basically the initial conditions that has been treated. So as I said, we want to solve the Einstein's equations. And for that, basically, in order to put the initial conditions, as I said before, we have to solve this the constraints equation, the Hamiltonian momentum constraint. So there, as you can see here in pink, there have been a couple, few papers already studying this. And basically, in these papers, what we are considering is this episode, no, this scenario where you have a large inhomogeneities either in the scalar field, or you have inhomogeneous kinetic in the kinetic the velocity, scalar field velocities, etc. So basically, what you do is you plug your configurations or large modes in phi or in phi dot, and then you solve this Hamiltonian constraint. And if you only put one of the two, either the gradients or kinetic terms, then you see one of these two terms is zero. Then I don't know. I think you can see my mouse now. So basically, this term here. So
Yes.
if you okay, very good. So if one of these two terms is zero, then very easily the momentum constraint is satisfied. So you only need to deal with this. However, now there are more clever algorithms that you can put whatever you want. You can put gradients and a scalar field metric and solve it iteratively, and you can also solve the initial condition for both. So basically, that's what we have been trained. So in a way, what we assume is, in this case, it's just a diagonal special metric, a conformal diagonal special metric, so conformally flat. That means that the perturbations in the gravity sector are only in the scalar curvature. So the scalar curvature basically will be the exponent multiplied here, right? So basically, this is the scalar curvature. And basically, they will give you this term here that is non-zero, that basically you have to solve. When you put, basically, you have to solve like some kind of Poisson equations in order to solve this equation. Okay? And basically, there are several assumptions that are implicit, somehow in this kind of condition. So, and these are the following. They are quite evident. So we assume that the universe can be modeled by general relativity. So we are not in the quantum gravity regime. We are in GR. We think that we assume that the universe is at least in average expanding. So maybe some region could be contracting or expanding, but at least what we simulate in average is expanding. That's what we assume. And the other is that there is UR, of course. So you have a potential like this. I don't see my mouse anymore, but it's okay. So if you have some kind of potential like this, then you are in a region of the universe where the field is in the inflationary part, meaning that you are not in the bottom of the potential, you are in the part where the potential is positive and more or less flat, that can sustain inflation for at least 60, right? So that's our minimal assumption that you need to take. And the other one is that will be important data at the end of the talk is this causal local dynamics, that basically we assume that if you put perturbations that are super Hubble, of course, perturbation can be sub-Hubble and super Hubble, you don't know, but what we assume is that yes, for cosmological perturbation theory, so basically you have super Hubble modes, these will be frozen until they re-enter the Hubble, the local Hubble patch of the simulation, and then they can start fluctuating or even collapsing, etc. Okay? But when there are super Hubble scales, they should not impact or they should not influence, in principle, the local, so the low scale dynamics. That's basically what we mean by locality in this case. Okay, so these are, I think, quite reasonable assumptions. So basically, we will do that. So we put all these configurations in a box. So in here, what I'm putting is the equation of state, just because this is a very nice variable. Because if this is goes to if W is equal to 1 in some region, that means that in these regions are strongly dominated by kinetic, so the kinetic field is dominating the energy budget. If you are in the green-orange part, it means that basically you are in a part of the universe where it's dominated by gradients. And eventually, if inflation starts, it should go into the W go to -1. So and then these patches will become blue. I mean, and this why this color plot that I chose here. And that's what we do. So basically, we choose this kind of simulation. So for example, everywhere is this inhomogeneous kination where it will transform into gradients. So this is just an illustration of evolution of a simulation, and you see that yes, at least for this case that I'm showing here, eventually there are some patches that become dominated by the scalar field, and finally the whole lattice is inflating, and inflation can start. Okay, so very good. So that's quite a nice representation or simulation. I'll be a bit more in detail. So basically, in these plots again, I show the equation of states, but now in a linear manner, where basically I'm looking at the upper plot. Basically, I'm drawing the density. Basically, so each vertical beam, let's say, is basically the density of where the universe. So basically, these more darkened regions means that basically the whole universe is dominated by kination, and then as T evolves, then so it starts evolving. It becomes more messy. So some regions start being more dominated by gradients or more kination, etc. But after 15 or 20 Hubble times, so you see that inflation has succeeded, and basically it's dominating and it's inflating everywhere in that picture. Of course, there are very interesting dynamics. So I don't want to go much into this, but yes, depending on if you have a large gradient, you form black holes indeed. So these are these resolved by Katie Club, and also in my own papers. I also in the first paper we also show these primordial black hole formations. Also in the paper by Linde and East, they also show these primordial black hole formations, but they actually don't. So for the question where inflation can start, they don't. Of course, inflation will not start inside the black hole, but in the surroundings, actually, the formation of black holes facilitates the beginning of inflation at the boundaries. As you can see here in this picture, in the upper second picture where I show this red circle. So basically, this is the formation of the black hole, the screenshot, and then you see on the boundaries, the equation of a state it's enhanced, no? So it goes to -1 into the boundaries. That means that the energy, that the fluctuations gets localized into inside the black hole, basically almost helping to homogenize the surroundings. And actually, it seems that inflation it starts easily when these black holes are formed. But again, this is our details of the rich phenomenology that can happen in these scenarios. Okay, so just to continue, so I'm gonna just say a few bullet points that we have learned with all these studies that we have done. So the first, as I said, black holes do not prevent inflation, most of the opposite. No? They can try to facilitate it. The other is that large field potentials work much better than small fields, and this is something that I'm gonna emphasize in the next slides. So large field inflations basically are fine. So we cannot say they are fine at all. While small fields, it can be difficult, and in those cases, we might say that inflation is fine-tuned. And in the other case, so convex potentials are better than concave. This is particular for small fields because as a large inflation, it doesn't matter. They basically seem to work very well for all of them. But for the small field potentials, convex potentials are better than concave. And this is a very nice paper that Joshua Aurrecoechea made also using numerical redistributions, and they can have a formula where you can more or less estimate whether this fine-tune is very severe or not. So I also recommend this paper very much. And so just let me focus a bit more on this small field and large field inflation. So basically, if you have a large gradient, so large gradients in a sub-Hubble or in a Hubble patch, of course, intuitively, what we do is basically the universe will tend to go to the mean value. So you have a maximum and a minimum, so it will be in the middle, let's say. So eventually, all this with the expansion of the universe, they will be redshifted. At the end, the universe in the Hubble patch will be more or less in the mean value at the beginning. Okay, this is imagine that you only have gradients. That's basically what you find. If you have kinetic terms, strong kinetic terms going either up or down the potential, or up or down basically the field value, what you find is that okay, the kinetic terms are suppressed by the Hubble expansion, so to a to the -6, something like that. So what you find is basically that there is a range where you can end up. So basically, if you start simulations at phi equals 0, for example, in the left potential, you can end up either basically if you have strong velocities to the right, for example, then you might end up the pre-inflationary phase already in the bottom of the potential, and then of course there you will not inflate. You are already in the reheating region, and you will not have enough periods of inflation. In the other hand, in the large field inflation, again, you can only move one or two Planck values in the field values, Planck field values. So basically, even if you are in the threshold or close to the threshold where you have these 60, 80 e-folds of inflation needed to explain the observations. So even if you have a large velocity, you move very little from this potential. So you will still have inflation. Maybe if you are really in the boundary, there will be some regions where you have no 60, maybe 55, something like that. But anyway, the parameter space that would explain our universe is huge. And in that sense, it's not fine-tuned at all. Okay? To be more clear, so there is this another paper by Raychaudhuri and Jerome Martin, Vincent Benin, and Cristian Joana, where basically they study also full numerical stimulation, but only kinetics or homogeneous kination. And actually, the results are compatible with the full numerical relativity with gradients. So I think the results are also very nice. Basically, in this plot, basically what you show is basically the potential. Basically, in the x you have the file, no, from -6 to 6. And here basically the potential of before. And the vertical axis, you have the velocity, the normalized velocity, which can have from plus the maximum velocity you can have to -1, right? And then basically they show that in the small field inflation, the ones in the left, there is a sweet spot where basically you can have this necessary 60 of inflation. This is the green and white part. But as soon as you have some kinetics, you can really be pushed out of this sweet spot, and then you will end up in this red or black region where basically you are not inflating, or inflation is lasts very, very little. However, in the right, again, it's the same explanation as before. So even this is stabilized inflation, the same potential as before, and centered at 0. If you are in the needed part, so basically around 5 or 10, around here's around 5, Planck values of the Planck masses. So basically, even if you have a strong velocity, so you go in the vertical direction, you see that basically the number of e-folds, you are still in the good region. So the parameter space that can explain, that can homogenize the universe is huge. You only need a patch value that is around 5 or larger. The 5 is MP. Right? So in that case, it's quite clear. Okay, let me go a bit faster. So basically, what we say is basically many models of inflation, especially those with large field models that are the ones that are more favored by Planck collaborations or by Planck observations, or Starobinsky model, non-minimal Higgs inflation, or the gamma tractor model, etc. That are the ones that are in the sweet spot in the plot. These are large field models, so they are very robust to initial conditions. So there seems to be no problem from. So there is no fine-tuning problem from this kind of potential. So all seems nice, all seems good. Okay, so but recently, last year and a couple of months ago, there was a couple of papers where, again, the analysts for Stein and collaborators, now with David Garfinkel, they showed that they claim that inflation cannot homogenize and isotropize the universe if now you have a strong whale curvature. So basically, if you have a strong gravitational perturbations, so basically that the whale tensor is also very large. In that situations, inflation might even not start, it might collapse, might recollapse into itself. And even if inflation starts, the whale curvature it will not decrease, it will not explain it will still be curved even at the end of inflation. So this was a bit of a puzzle. And then they also show some numerical relativity codes that they enforce basically they corroborate what they're trying to say. And it was a puzzle for us. So of course we wanted to verify this, and I was going to show now some papers that basically contradict this view. And basically at the end, so I'm going to tell you now that basically what I believe in their case the problem is in the initial conditions. So I think in the initial condition, all these assumptions that I assumed before, there is one that is not fulfilled. So they assume non-local interactions. But I will go more into this at the end of this talk. And if this is case, then that is true, then they are right. But it's not because you have a large whale curvature. So I will show actually that whale curvatures do not impede inflation, do not prohibit the beginning of inflation. So in order to just make it more just to explain it better. So basically what they do is just define the wild tensor, and then the wild curvatures and churn point ranking invariants, so this C and P and C are just the contraction of the wild tensor and the Y with its dual. So for now on, I will call it wild curvatures C and P. So both wild curvatures, right? You mean I understand both. And basically the idea is that this well curvature hypothesis tells us that after the quantum gravity regime, all the degrees of freedom should be mixed up. So basically, you should imagine that both the scalar field and kinetic terms and C and P well curvature should be of the order of the Hubble rate. So it should be large, could be codominant to each other. And at the end of inflation, if we want to satisfy CMP constraint, it need to be smaller than 10 to the minus 10. Okay, so the temperature anisotropies. Okay, so basically now we have to create new initial conditions, taking into account that we want large and large C and P curvatures. And basically what we do is, again, we have initial constitutions, and then the paper by Matthew Ely and Katie Claude, Eugene Lim, and collaborators. So basically what they do is this kind of approach. So again, they input some inhomogeneous kinetic and so they put gradients and kinetic terms. So basically now you have to iterate both the Hamiltonian momentum constraint, and in order, basically, you fix the scale factor equal to 0. So you have, in this slide, you will just have a no scalar curvature. Instead, you will solve your constraints equations by having perturbations. So in their simulations, the initial condition, they still assume a conformal flat spacetime. But all the curvatures will be in the time derivative. So will be this AJ that are basically so even in your hypersurface, your metric is conformally flat. You will put a strong kinetic term that as soon as you start evolving, you will basically have the curvatures mix between kinetics and gravity. That's how they solve the constraint. So they have an algorithm that they solve this equation. Okay, so basically now you have a strong initial conditions with gravitational modes, let's say, and strong gradients and kinetic terms in the initial conditions. So basically the question now is, does inflation last 6 e-folds, and does the CP become smaller than 10 to minus 10 at the end, or at least during inflation? Okay? And the answer is, again, with large field models, yes. And with small field models, no. There are cases where actually this doesn't happen. So it's basically the same conclusion. And this you can see in the plot in the right. For example, large field model is plotted with these dashed lines. So this gamma plot is the gamma of the potential. So when the universe is dominated by the potential, this is close to 1. Okay, so in the large field model, you start in a place where completely are irrelevant, so the potential is subdominant. But then as the universe expands, eventually the potential will start become more and more important until inflation starts, and you see that basically it's sustained for here is 10 e-folds, but just because here we stop the simulation, right? And then if you look at this wild and churn point ranking curvatures, the CP well curvatures in the plotting below, you can see that in the dashed line, so basically you start the order 1, so this is the log in the y-axis, so it basically starts increasing, and when inflation starts, they have an exponential decay that basically, and after 7, 8 e-folds, number n is the number of e-folds, you are already in a log 10 to minus 10. you explain basically the observation. On the contrary, in the small field is the opposite. Actually, even you can be in a place where inflation should start, so you are basically dominated by the potential, but because you have this gradient and this curvature, the field can be pushed out of this sweet spot and really basically having a premature reheating. And basically that only lasts 16 foot. That's what we see in the solid lines, and yes, indeed, the small field models, as we know, can be fine-tuned for this kind of initial conditions. It's a problem for this kind of inflationary model. But large field models, as I argued before, they work very well. They don't have this fine-tuning. Okay, so let me continue with the latest paper. So that's on my own. So that is accepted just now. So it's in the archive for a couple of months. And basically here would I have a different approach. So now what I took is a completely homogeneous metric. So here I don't assume that this is flat. So I just put inhomogeneities in the metric tensor, in the conformal metric tensor. And basically from that, I solved the first equations, and I just solve for a kination or gradients in order to satisfy the question. So it's much easier. In that case, so initially I don't consider shear. So this AJ, I consider 0, but because you have a strong gravities, strong modes in the gradient and also the scalar field. Okay, yes, I'm about to finish. So basically these AJs will enhance very much. So as we see, basically this is some figures, basically snapshots of one of the simulations that I made. So you will see that again, after 3 folds of inflation has started. If you look at the equation of state in the right, and basically again, what I was saying before, that the displacement of the scalar field, the mean average field in the Hubble patch is not larger than 1. So that's one of the reasons why large field inflation was very well. And this rho shear and the rho is just this term. So the red term that I mark here will be this rho R. So this is the gravitational, the energy associated to curvature in a way. And the rho shear is basically this AJ that at the beginning we consider 0, but they are sourced from the dynamics. And as you see, after 1 e-fold, 2 e-fold, so they co-dominate with the scalar field. So there are regions of the space where it's 5 times larger than the scalar field. So that explains that all these terms are sourced. Even if you consider 0 at the beginning, then it will be sourced. So it's no problem. Okay, so just to finalize, so the well curvature CMP also similar as before. We start with is proportional to the Hubble radius. During the pre-inflationary phase, they grow in respect to the Hubble rate, yes. But once inflation starts, they start decaying at a power law. So the C is at a to the minus 4, this P curvature is to the minus 5, and then this Ricci depends on the quantities, no? But it's more or less 3/2, right? A to the minus 3/2. This is the power law with the initial conditions that we do, right? So in that sense, okay, here we show that basically, yes, so the take-home message that I want to emphasize is both inhomogeneities in the gradients and the gradient terms very large, so basically you dominate the dynamics with this. This does not block inflation. Inflation can begin and when you reshift these quantities. So this is not true that this blocks inflation. And also these well and P curvatures, also even if they are very large, they can even be even larger during the pre-inflationary era. But when inflation starts, they will decay, and in just let's say 10 e-folds of inflation, they will be smaller than 10 to the minus 10, or will depend on its needs, but they decay fast. So it's not an issue for explaining the CMB, even if you have a strong weight and P curvatures in the beginning. So this is the first take-home message. The second, of course, is I put this an asterisk because this is true for large field models of inflation. As I said, these are very robust. However, for small field models, they are not. So you have to go model how this sweet region is really narrow or not, and this depends on a lot on the model. So if you are considering small field models, you have to have this thinking in your back on your mind. Maybe fine tuning will be a problem. I need to think a way how to solve it. Okay? So this is the take-home message. And now probably what you are questioning, okay, but in the papers, they also do numerical relativity simulations, and they claim basically that this doesn't happen. So why is that? Okay, so in my paper, I already point a bit into that in my last paper, but we are working in order to make a proper answer to these articles. And basically, yeah, so what they show is basically, for example, in the slow contraction, they show that they are very nice, so it works very well. So after 10 numerical, this is a computational time, but basically, so even if you start a very inhomogeneous state, low contraction, the alternative model of inflation, it seems to work very well. But when they call for inflation, even when you have scalar fields that are subdominant, and you are dominated by shear, they seem to show that basically inflation cannot be, it basically crashes and everything becomes completely homogeneous, and basically it's very fine, right? They are also simulated the large field model, by the way. So what's happening here? Why is this occurring? And after looking carefully to the assumptions, or at least how they construct the initial data, what I found out that basically, as I said before, is that they violate the last of our assumptions. So basically, this causal local dynamics, they are not. They impose on very large, very strong shear mode that are super half scale. So let me just go here. So basically, this ZAB is basically, or AIJ, because we use a different formalism, but at the end they are very similar. So basically, yes. So basically, they put inhomogeneities in the AIJ, which is very, very fine. So basically, you have to see that the cos, they have this cosinus where you have basically a mode that is as large as the box. And the thing is that these modes are time derivatives of the metric. So if you put time derivatives of the metric, you have to be, in my opinion, you have to be careful whether you put this as super Hubble or sub Hubble, because what they do is basically they use a box that is like 70 times 2 pi the Hubble radius. So this zeta 0, this symbol. I think it's sigma zeta, I don't know. This sigma that is minus 3 over k0. This is basically the Hubble radius. So basically their box is huge. It's more than 70 Hubble patches. And then they have a very large metric shear perturbations that evolve at super Hubble scales. So that's why, and I think this is the, yes, okay. Very good, very good. So basically, I finished now. So basically, that's my explanation why I do this, and basically because when they do it for the slow contraction paper, it's basically the opposite. Basically, they consider a perturbation as a Hubble size, which I think it should be. But for inflation, they consider this very large box with very large super Hubble dynamic modes in the metric. Okay? And then if you think physically, basically, imagine a gravitational wave. Basically, is constraining in one dimension and elongating in the other way. If you have a super Hubble mode, basically along one direction, basically you might the shear might overpower the initial expansion rate. So that's why here I put actually this in orange, because if you have this super Hubble metric perturbation, so if you are in the dimension, in the physical dimension that you are contracting, because this is evolving shear mode, you might be actually overpowering the expansion rates around this direction, and this would explain why these gradients at these terms becomes large, because of course then you are not reshifting, you are blue shifting them because you are now contracting. So I think that would be an explanation. However, this has to be tested. So as I put here, this is a discrepancy. This is a possible reason for the discrepancy, and this have to be. We have to make a proper response and a proper analysis in order to confirm that that's the case. And yes, so basically, stay tuned, because we are try to answer more properly this. And anyway, that's it. And I thank you, and I show basically. I think all my collaborators from China, from Shippy, and all my group.